Okay, so welcome everybody to the ICS Theoretical Astrophysics seminar. Today we're very happy to have Pierre Fleury as our speaker. So Pierre did his PhD at IAP in Paris, then moved on to first postdoc in Geneva, in Cape Town, and then a second postdoc in Geneva. Sorry about that. And now he's in Madrid with the Junior Leader Fellowship of La Caixa Foundation. And Pierre is going to talk today about Horndeski and the Sirens, a very poetic title. So Pierre, thank you very much. You have the floor.
Thank you very much, Hermes, for this introduction. And so, as you said, I'm currently based in Madrid, but this project I'm going to talk about has been done in collaboration with former colleagues in Geneva, who are Charles Dalland, who is a PhD student there, and Lucas Lambrizer, who is his PhD supervisor. So the references on which this presentation is based are indicated here. And I would like to stress the very important role that's been played by Charles in this project, and in particular in all the technical, well, most of the technical parts of this second article. All right, so let's go with the menu. The general topic of this presentation will be alternative theories of gravity, and how to test them using gravitational wave observations. So I will start with a very general introduction where I will motivate this class of questions from a cosmological point of view. I will then explain what these standard sirens are and how we can use them to test gravity. And then I will move on to some more technical aspects where I will focus on a particular theory of gravity that's called Horndeski theory of gravity, where I will explore in details how gravitational waves are propagating. Right. So I think that a possible starting point when we talk about alternative theories of gravity is cosmology, and in particular, the fact that we know since the end of the 90s that the expansion of the universe is accelerating. So this means that when you observe a distant galaxy, you see it receding from you. This is the expansion of the universe, and the velocity increases with time. And so I think that most of you have heard about that, I hope. But when you think about it, of course, this is an extremely counterintuitive phenomenon, because we know that gravity is supposed to be attractive. So if the expansion of the universe is accelerating, that means that there should exist some kind of repulsive form of gravity, which is usually not the one that we describe with our theories of gravity. But in fact, from the theoretical point of view, having some kind of repulsive gravity is not something that is too hard to model. If you start from the good old Newtonian theory of gravity, where the gravitational potential is related to the local density of matter by the Poisson equation, so this tells you that when you have an overdensity of matter, you create a potential well where things fall in. So how to have repulsive gravity? Well, we can just add a negative term to the right-hand side, which we call the cosmological constant. So in essence, what this means is that you would add to, suppose you have two galaxies that are creating their potential wells where things could fall in, you will add to that a kind of global, instead of a potential well, a global potential trough, which would make things want to recede from each other. So this is how you can get a notion of repulsive gravity, even in Newton's theory. So of course, the Newtonian theory of gravity is not really up to date. So the currently accepted theory to describe gravity is Einstein's general relativity. But you have exactly the same phenomenon in Einstein's theory. So in the sense that you can add a term like this, which we call the cosmological constant, and that would create, in the language of general relativity, a notion of space-time curvature that would make objects want to recede from each other. So now, a possibility is to add such a term, a cosmological constant, by hand to explain the accelerated expansion of the universe. In that sense, it could be a new constant of nature. But another possibility is to add a form of matter that would create the same kind of effect. And this is not that exotic. If you add to the content of the universe a form of matter like a new physical field, like a scalar field, for example. Think of the Higgs boson, for example. Something like this could play that role in principle, in theory. So if you add such a field and that it's very homogeneous and almost static, it turns out that its gravitational effect is similar to the cosmological constant. So this would create a form of repulsive gravity. So in that spirit, that would mean that, so if we adopted that idea, there would be some kind of fluid, some kind of field in which matter is placed, and that would tend to repel things. And we call that, in that context, dark energy. Now, if you add a new field, a new physics field, it's also quite natural to wonder whether this field could be coupled to gravity in a weird way. And there are many couplings that would be possible. So if it happens that this new physical field that would play the role of dark energy is coupled to gravity in a non-trivial way, you would modify the equation of motion of gravity, which was here the initial one, the Einstein's theory, the Einstein's field equation. You could add terms that would modify that. In other words, that would modify the way matter acts on the geometry of space and time. When you have such a thing, you would talk more about modified gravity. And in the current cosmological context, there are many attempts to model the accelerated expansion of the universe using either of these effects, either having this kind of dark energy or modifying the behavior of gravity. Right. But now, when you do that, when you allow gravity to have new degrees of freedom, to be generally modified with respect to general relativity, you open gravity Pandora's box. And many, many weird things can happen. For example, if you allow gravitation to be different from general relativity, one thing that can happen is that the gravitational constant, Newton's constant, that rules the gravitational interaction between, for example, the Earth and the Moon, could be something that changes with time. So instead of having a constant, you would have a variable Newton's coupling. What else can happen? In general relativity, gravity doesn't only act on matter, it also acts on light. So matter is able to deflect the path of light and also to change in general its behavior. One of the possible effect is called the Shapiro effect. So suppose that you exchange a light signal with a spacecraft. Well, the time that it takes for the signal to go back and forth to this spacecraft will depend on the gravitational fields that are experienced by light. And for example, if you have the sun that's close to the trajectory of light, it will take a bit more time for light to do this going back and forth. So this is called the Shapiro effect, and the time delay that would be imprinted by the presence, in this case, of the sun, will be proportional in general relativity to the Newton's constant. But if you go beyond general relativity, it could be that this constant is not the same as the one that is ruling the matter-matter interaction. So you would have, in this context, in principle, you could have a matter-light interaction that's different from the matter-matter interaction. What else can happen? Since 2015, we have observed gravitational waves. So they are waves of gravity itself. And in general relativity, these gravitational waves are propagating at the same speed as light. In other theories, it could be that they don't. So this is another thing that could happen. And finally, something else that could happen when you go beyond general relativity is that these gravitational waves, which have an energy that would tend to dilute as they propagate, just like any wave, the energy would dilute as proportionally to the area of the wave fronts. You could have a different kind of dilution. And this dilution will be controlled by another gravitational constant that in principle should be the one of the same one as the Newton's constant. But in that case, so the gravity interaction could be different, could depend on time, and yeah, differ from these other ones. So this is what I mean by opening Pandora's box. There are so many effects that could be different from general relativity if you allow your theory to be richer. Fortunately, we are testing very actively these things. And for example, the time variation of Newton's constant, for example, so that controls the interaction between the Earth and the Moon, has been very intensely tested using what we call lunar laser ranging. So by exchanging laser signals with the Moon, we could test what's the possible time evolution of Newton's constants. And the current constraints that were put by this paper here indicate that the time evolution is extremely slow. Actually, to have a significant variation of G Newton, we should at best wait for more than 1,000 times the age of the universe. So we can consider to a good approximation that this one is a constant. What about this light-matter interaction? So the spacecraft that I have put in the slide here is actually the Cassini spacecraft that's been sent in at the end of the 90s, I think, or the beginning of the 20s. So by exchanging light signals with this Cassini spacecraft when it was on its way to Saturn, the magnitude of that effect, of this time delay that can be observed with signals going back and forth, has been very well measured, and it's been shown that this gravity, so this matter-light interaction, is ruled by a constant that doesn't differ from the Newton's constant by more than a part in 100,000. So this one is essentially the same as Newton's constant with current constraints. What about the speed of gravitational waves? So you have probably heard that in 2017, it has been observed a gravitational wave signal that's been emitted by a merger of two neutron stars. And so this merger of two neutron stars emitted light, so a gamma ray burst, and a gravitational wave that were observed with a few seconds of interval, which means that the speed of gravity and the speed of light cannot differ by more than, in that case, a part in 10 to the 15. So we can also safely consider that the speed of gravitational waves is the speed of light. But now this one, how the amplitude of gravitational wave evolves with time as they propagate, is something that is not constrained yet. So is there a gravitational constant that is different from for the gravity-gravity interaction? So something that would differ from the matter-matter interaction or for the matter-light interaction? This is still an open question, and this is what I'm going to focus on in the rest of this talk. So before I move on, is there any question on that? Please, Shai.
Can I ask? When we see descriptions like parametrized post-Newtonian, are these explanations, are they equivalent to statements in PPN, or about something more?
Yes, they are. So these statements are associated with post-Newtonian parameters. So I express them like this to have a description that is easier to the eye, but yes, they are completely equivalent to a parameterized post-Newtonian approach, yes. For example, this one is associated with the so-called gamma parameter in the post-Newtonian description. Any other question? Okay, so if not, I will now move on to how we could potentially use, which observations could be used to constrain this notion of gravitational wave, gravitational constants. And these are standard sirens. So standard sirens, so they are not these ones, because these ones are not that standard. You know, so I've been told when I was giving a talk in IAP, I think it was a year ago, that so I thought that these things were called harpies in English, but actually no. In this painting, these are sirens, because it has never been said in the Odyssey that sirens were half fish, half human beings. So in fact, these were representations of sirens that existed in art before Disney, I think. So the other of these ones I'm going to talk about, the standard sirens I'm going to talk about, are actually mergers of compact objects. So what are these things? When you have two compact objects like two black holes or two neutron stars that are orbiting close to each other and that eventually merge, they emit gravitational waves. And it turns out that this gravitational wave signal in itself allows us to extract the distance to these objects, to this merger. So you can see that in the signal that you would receive with an interferometer, you can observe, of course, the amplitude of the signal that changes with time, and also the phase. The amplitude is dictated by the ratio of a notion of gravitational luminosity that we call here the chirp mass. So this is a quantity that characterizes the system and that tells you how much energy is emitted under the form of gravitational waves. And it is rescaled by a notion of distance, which I will call here dg, like the gravitational distance, that dilutes the signal as it propagates. Now, when you observe the phase of the gravitational wave, it turns out that its time evolution, or let's say the time evolution of the frequency during the inspiral phase here, is directly proportional to this chirp mass that controls the amplitude. So when you observe the full signal, you can actually extract directly this notion of distance. So observing gravitational wave signals emitted by binary systems like this allows you to measure their distance. And this is why they are called standard sirens, by analogy with standard candles that we have in cosmology that would be, for example, Cepheids or supernovae, that are objects of the distance of which you can measure also. So why is that interesting? Well, a first very important interest of such distance measurements is that you can construct, in principle, a Hubble diagram with it. So what this means is that if you have such a merger of compact objects that you observe, so from which you observe gravitational waves, so from which you can measure the distance, dg, and if you can localize the galaxy in which it is located, and that you can measure the redshift of this galaxy, you can plot, you can make this plot where you have the distance as a function of the redshift. And this is what we call the Hubble diagram. So this is very important, observable in cosmology. For example, the initial slope of that diagram represents the expansion rate today of the universe. So this famous h0 quantity that quantifies how fast our universe is expanding. If you look then at higher redshift, you can actually reconstruct like this the history of the expansion of the universe, which allows you to infer, for example, the density of matter, etc., or even the cosmological constant. So the very important thing with standard sirens is that with instruments like the laser interferometer space antenna, LISA, we will be able to go up to very high redshift, such as redshift 10, which is completely inaccessible with standard candles. So observing gravitational waves like this would allow us to reconstruct the history of the universe up to very, very early times. But that's not all. And here, let me go back to the initial subject, which was testing gravity. In general relativity, this gravitational distance is the same as the luminosity distance that you would measure with standard candles, such as supernovae or Cepheids. But if you are in alternative theories of gravity, this is not necessarily the case. And this goes back to this thing I was saying at the beginning. If you have a theory where this notion of gravitational wave, gravitational constant changes with time, this will tend to rescale the distance that you are measuring, because it changes the way the energy of gravitational waves dilute as they propagate. So in a very wide class of theories, when you work in a homogeneous universe, we look at gravitational waves propagating in a homogeneous universe, the ratio between the gravitational distance and the electromagnetic distance is simply given by the ratio between the gravitational constant at emission and at observation. So this means that if you have such an evolution, you could make the difference between gravitational waves, the gravitational wave Hubble diagram and the supernova Hubble diagram. And by measuring the difference between these two curves, you could have access to that thing, to a possible evolution of the gravitational wave, gravitational constant. Right, so that is the motivation for such an observable, and this is how we could fill the gap that is missing in testing theories of gravity. But the universe is not homogeneous, which was something that was used to derive the previous equation. And so the people who know me here know that I've got a bit of an obsession for the homogeneous universe. So what happens in the real universe? What happens if gravitational waves are propagating in a more realistic universe than just this homogeneous model that we usually use? So the first thing that can happen, and actually that we consider necessary, is that the emission process of gravitational waves is not changed too much. Because if I'm starting to modify the way gravity is acting, and I'm saying that gravitational wave emitters are still standard sirens, I have to assume that the emission mechanism is not too altered by the modifications of gravity. And this is usually justified by invoking what we call screening mechanisms. So we would imagine that there exist mechanisms that allow deviations from general relativity to remain hidden in very high density regions, like, for example, where gravitational waves are emitted. Okay, why not? But if it's the case, when the gravitational wave goes, let's say, close to a galaxy that might be screened as well, what happens? Is its propagation still the same as what we considered before? Is it changed? If you go close to a galaxy, you might also have gravitational lensing, just like there is gravitational lensing of electromagnetic signals. Is that the same as the one that we have with light, or is it different? If you have other degrees of freedom for gravity, like, for example, another scalar field, it might happen that the gravitational waves decay into these other degrees of freedom. Maybe gravitational waves would convert into other waves that are not the ones that we are expected to measure. Does that change the amplitude of gravitational waves? How much? And finally, if this part is screened and this part is screened, what may happen that where we observe gravitational waves, it's screened as well. Is the screening the same as in the emission at the emission place where the gravitational wave is propagating? So all these questions could, in principle, all these things could, in principle, change the gravitational wave distance that we are measuring with these standard sirens. So the question, I think, is what is the gravitational wave distance in the real universe instead of an idealized homogeneous universe? Before I move on to more technical things, are there questions? Maybe I should go back to this slide. Do you have questions on these motivations? Please go ahead. Nothing? All right. So to answer this question, we have to go a bit more quantitative. And for that, we need at least a model for gravity, so that wouldn't be general relativity, so something that would go beyond general relativity, but that is still a well-defined theory. And so what I'm going to consider in the following is the so-called Horndeski theory of gravity. So Gregory Horndeski was a physicist who in the 70s during his PhD derived what is the most general so-called scalar tensor theory of gravity. So he did that during his PhD, and the paper was left mostly unnoticed. Then he got a tenure position just after his PhD. He did research there during, I think, 8 years. And then he went back to his initial passion, that was painting. So this slide here shows one of the painting of Gregory Horndeski that is called the fireball approaches. And so he's got a very important production of paintings. And it turns out that in the 2015 or something like this, his theory was rediscovered and became very trendy in cosmology. And so a friend of him told him, well, you know, one day I went to this conference and people started talking about Horndeski theories of gravity, so that he didn't know. So this is how Horndeski, who was a painter for decades, then started again during a bit of theory. So there are articles now that are still written by Gregory Horndeski, and as a parallel activity to his painting art activity. So what are these Horndeski theories? So the Horndeski theory is a class of gravity theories which start from general relativity, to which you will add an extra scalar field. So this scalar field, you could see it as dark energy, so as the thing that is responsible for the accelerated expansion of the universe. And that can be coupled non-trivially, so we say non-minimally, to gravity, space-time geometry. You could see also this theory as an effective behavior of some high-energy theories. For example, theories that have extra dimensions. When you compactify these extra dimensions, they might result into additional scalar fields in the effective gravity theory that we experience in our four-dimensional world. What I'm going to call reduced Horndeski theories are the part of these Horndeski theories such that gravitational waves propagate at the speed of light, because we have very strong constraints on that. So the resulting Lagrangian looks like that. So you've got a Lagrangian of reduced Horndeski theories that depends on the space-time geometry, so the metric G mu nu, this new scalar field. The way it couples to gravity it can be understood directly with that part here, which is the action of general relativity. So here, this is the Ricci scalar. That would be coupled to, well, that would be multiplied with a function of this scalar field that would play the role of this effective gravitational constant. In other words, for those who are familiar with that, this would be the effective Planck mass, squared Planck mass of the gravity theory. So now the dynamics of this scalar field can be ruled by a general function here, where x is the kinetic term of the scalar field. So this is called k essence. And the last term here that is allowed is called cubic Galilean, or sometimes called kinetic gravitational braiding, just to have this wonderful KGB abbreviation. And this term allows you in particular to have screening mechanisms that I talked about previously. So this is the general action that I will be interested in. And you see that it is very, very general in the sense that there are a lot of freedom in this. This is a free function, this is a free function, and this one as well. So it's a theory that is defined by free functions and not even free parameters. So there is a lot of freedom in its behavior. Right. So I'm interested in gravitational waves in such theory. So what I'm going to do is I will linearize the equations of motion of that theory. I will linearize it in terms of both the degrees of freedom that we have, that are the scalar field, and the metric field. So you could think of these background quantities as representing the astrophysical and cosmological background where the waves are going to propagate. So, for example, the gravitational field created by a galaxy, by the sun, etc., etc. And these will represent gravitational waves in general. And I say gravitational waves because gravity here is described at the same time by the scalar field and by the metric field. So both of these quantities represent parts of a gravitational wave in this class of theories. When you write down the equations of motion, the linearized equations of motion for this theory, formally it can take the following form. So here what I did is I split the equation of motion into terms that contain second derivatives, first derivatives, and no derivatives. These terms here are complicated expressions that I'm not going to give. What's important is just the fact that they have this general form. I've written them as matrices because the equations of motion for the scalar perturbation and for the metric perturbation are coupled with each other. That means that, for example, in the scalar equation of motion, that would be the first line here, you would have terms that contains, for example, second derivatives of the metric field. That would be, for example, given by that term. Right? So they are completely coupled. That's why they take a matrix form. Now, why did I make a division between the terms with a different order of derivatives? So these ones, the terms with second derivatives, are the kinetic terms. They are the ones that are the dynamical properties of these perturbations. The terms with only one derivative, I call them amplitude terms, because they are the ones that are going to rule how the amplitude of the waves are changing as they propagate. And finally, the mass terms would be terms that would change the dispersion relation. And I'm going to neglect them because I'm going to work in the following, in the so-called iconal approximation, where we consider that these waves have a very short wavelength. So they evolve on scales that are much shorter, much smaller than the typical length scales over which the background is evolving. And therefore, anytime you have a derivative of the perturbations, you've got a term that is very large. So these terms are much larger than those ones that are themselves much larger than those ones. And this is why I'm going to neglect these mass-like terms in the following. Now, I insisted on the fact that these equations of motion are coupled. And this is something we don't like, especially in the kinetic terms. When you want to solve, say, an equation of motion with two variables, x of t, y of t, and you have second derivatives of y that are contaminating the equation for x and vice versa, this is something which is really uncomfortable to solve. So what we do in general is that we try to diagonalize this kinetic matrix here, to have equations of motion that are decoupled at the second order derivative level. And this can be done at the cost of defining a new tensor degree of freedom. So the idea here is that these two quantities are not the most fundamental degrees of freedom of the linearized theory, because they are coupled in their kinetic terms. But if you define this quantity that I call here gamma mu nu, that is mixing the metric perturbation and the scalar perturbation, here a hat represents the so-called trace reversed transformation of a tensor. This is not that important, but the important thing is that this guy mixes these two terms. So if you do that and you replace in this equation of motion h by gamma, then you get an equation of motion that is diagonalized at the kinetic level. This means that gamma is the real tensor degree of freedom of the theory. And this will be very important in the following. And before I move on, are there questions? I know this is a bit technical, and I hope that I'm not boring you to death, but this is this was the only real technical slide of the talk. Okay, so no questions. So once we are here, the idea is to use the resulting equation of motion, where we have diagonalized the kinetic terms, so in terms of delta phi and gamma. So use that to obtain the properties of gravitational wave propagation. Okay, so in that spirit, the kinetic terms are going to drive the dispersion relations of scalar waves and tensor waves. What I'm going to talk, what I'm going to call tensor waves will be waves in terms of this gamma. And these terms will drive their amplitude. In particular, the extra diagonal terms are the ones that will encode the interactions. They will tell us how much energy would be exchanged between the scalar waves and the tensor waves. Right. So let's go in more details. Let's talk about these scalar and tensor gravitational waves. How do we do that in practice? I'm also going in the details, but I think this is interesting stuff. So how do we do that? Usually, the technique is to consider ensatse, for the scalar tensor perturbations, where we would split the amplitude and the phase. So here, the complex exponentials depend on two phases: v, that would be the phase of the scalar wave, and w, that would be the phase of the tensor wave. They are not necessarily the same, because in general, these waves are not going to propagate at the same velocity. The assumption is also in the framework of this so-called diagonal approximation that the amplitudes are varying much slower than the phase. From the phases, you can define a notion of wave 4 vector, right? So that would dictate, that would be tangent to the world lines that the waves are following. So by taking the gradients of the phases, we obtain notions of wave vectors. And from the kinetic parts of the equation of motion, we can deduce, we can deduce the dispersion relations. So for example, the one of tensor waves, so the dispersion relation for this wave, for this perturbation, is extremely simple, because this tensor turns out to be very simple. And what it tells you is that the wave 4 vector is a null vector. What this means is that tensor waves are propagating at the speed of light, and they are following null geodesics, just like light. This is not that surprising, because we started from a restricted class of theory where we expect gravitational waves to propagate at the speed of light. So we are reassured of finding that property here. What about scalar waves? So now, in this case, a bit more complicated. The scalar waves, for scalar waves, the kinetic tensor is not that simple. And in general, it tells you that, that scalar waves are not propagating at the speed of light. It may propagate at a speed cs here. That depends in a complicated manner on the coupling functions of the theory. So they can be luminal or subluminal, which means that even if we started from a theory where we thought that gravitational waves would propagate at the speed of light, there is still a part of them, the scalar part, that is not necessarily propagating at the speed of light. Okay. To be a bit more concrete, what does it mean to have tensor waves and scalar waves? All right. Oh, no, sorry. I have to make a small parenthesis here about under which conditions the scalar waves are luminal. And I think because I might be a bit short on time, I will skip that. And if you have questions about it, I will go back to it in the following. So let me skip this technical detail. Okay, okay. I would like to explain a bit what I mean by scalar and tensor waves and what it means in practice. Okay, so gravitational waves in general, you have probably seen that picture before. So they are observed with interferometers through the motion of mirrors in this interferometer. The idea, imagine if you have a mirror that is here and a mirror that is here, and that you use that as an interferometer with a beam splitter that would send light here and light here. The idea is that you measure the dephasing of the two light signals emitted in one direction or the other direction from the motion of the mirrors. The mirrors are moving because gravitational waves are exerting tidal forces on the interferometer. So gravitational waves are just propagating tidal forces that we can measure. In the language of general relativity, they are just Riemann curvature perturbations that we can observe through motion of mirrors. So this is really a kind of equivalent as having, for example, here the moon that appears, and then that would progressively disappear and reappear here. So you've got tidal forces just like in standard situations of gravity. This would be for tensor waves. Now, in our case, what happens in the case of Horndeski theories, the curvature perturbations that are given by the metric perturbation will have two different components. Because gamma depends on h and phi, in reverse, this h, so the metric perturbation, depends on the tensor wave and on the scalar wave. So we'll have curvature perturbations, tidal forces that come from both the tensor wave and the scalar wave. The tensor waves are the ones that we are used to, the ones that I showed in the previous slide. They have two polarizations, and when you have a ring of particles that experience such a tensor wave, they will be transformed into an ellipse and back into an ellipse in the other direction, etc. You have this other polarization that's called the cross polarization that does the same, but along an axis inclined by 45 degrees. What happens for these scalar waves? In that case, it's a bit different. The scalar waves are creating, in general, some triaxial tidal forces, which means that when you have a scalar wave that's reaching a sphere of particles, it will distort it into a triaxial ellipsoid in general. There is a simpler case, though, which is when in the class of theories where even the scalar waves are propagating at the speed of light, in that case, the tidal forces created by the scalar wave are transverse, just like the ones that we have for the tensor waves. And they just transform a ring of particle into a bigger ring, and then a smaller ring, and a bigger ring, etc., which we call usually a breathing mode. So this is really what you would expect in general from, in principle, a priori, from a scalar wave. But note that this is not the most general case. Okay, so I hope that I have clarified what I mean by scalar or tensor waves. They would have a different notion of polarization when you receive them. Now, back to the thing we are interested in. How do their amplitude change? So from the linearized equations of motion and from the ansatz that I have given for the scalar and tensor waves, you can derive two coupled amplitude equations. And they take in general that form. So for the scalar waves, you would have, so this first part here would represent the free propagation of scalar and tensor waves. So with differential operators ds and dt, whose expression is not necessary in the following, is applied on the scalar and tensor amplitude. And you would have interaction terms that would tell you how the tensor waves are feeding the scalar waves and vice versa here. All right. Now, what happens? Let's distinguish between two cases. If the scalar wave is luminal, so if it is in the class of theories where the scalar waves are propagating at the speed of light, then the phases are the same. And I can remove these terms, I can simplify by these terms here. Besides, it turns out it's a bit of a coincidence, I think. I don't know how fundamental it is, but in that specific case, the interaction terms actually vanish. And you are left with two waves that are propagating without seeing each other. So in that situation, in that classes of theories, the scalar waves are completely irrelevant because they wouldn't interact with the tensor waves. Besides, it's very likely that they are not even emitted because there are strong constraints on that coming from the observation of pulsar timing. So we can, in these theories, even if there are modifications of the way gravity is acting, and even if there is an extra degree of freedom, which is a scalar, you don't care about it. And the only thing that happens is that the way this amplitude changes as the wave propagates goes like that. So the amplitude is rescaled by this notion of gravitational distance, which differs from the luminosity distance by the same ratio as the one I talked about at the very beginning of this presentation. So in these classes of theories where the scalar waves propagating at the speed of light, we recover what was predicted in the homogeneous universe. And we'll discuss that a bit more in the next slide. What happens now if the scalar waves are non-luminal? In that case, the waves are not in phase. And in principle, the equations are a bit harder to solve. But although I realized that just a few days ago, thanks to a private conversation with Jose Maria Ezgaga, who must be acknowledged at this moment of the presentation, it turns out that when you do the full calculation, the interactions, even if they are non-zero, are suppressed by the fact that the waves are not in phase. And in the end, you recover exactly the same results as the one as in the previous situation. So whether or not the scalar waves are propagating at the speed of light, we still have the same kind of results. Scalar waves are mostly irrelevant. I didn't say it, but the gravitational wave polarization is parallel transported. And the evolution of the amplitude of the tensor waves that we are measuring in interferometers is given by this formula here. Now, what are the consequences of that from the point of view of testing gravity using gravitational wave observations? In principle, this confirms that we could use this formula. But what I would like to emphasize is that now we're talking about such a quantity, the gravitational constant of gravitational waves at the point of emission and at the point of observations, which means that these quantities are very local. And so if you have gravitational waves that are emitted, so you have standard sirens that are in galaxies where they experience a different value for the scalar field, so this additional field of gravity, it may completely, so the fact that these may be different for different galaxies may completely wash out the effect of a possible time evolution of this scalar field. So what I really want to emphasize here is that although this formula that I showed at the beginning remains correct in the inhomogeneous universe, now it is very sensitive in principle to inhomogeneities. And this may be very dangerous, may add a very important source of noise in gravitational wave observations in the perspective of testing a potential time evolution of this guy with cosmic times, right? Was that clear? Feel that I've not been particularly crystal in that. Okay, so this brings me to a summary of this work. So the questions that I asked at the beginning were: what happens for gravitational waves in Horndeski theories in that case when they propagate in an inhomogeneous universe? So is there lensing? Yes, there is, and it's the same as light because gravitational waves are propagating along null geodesics. So all what is done for light can be applied for gravitational waves. Is there conversion into scalar waves in that case? If the scalar waves are luminal, no. If they are not, it is negligible anyway. And what is the gravitational wave distance? Well, it is given by the standard luminosity distance, but corrected by this ratio of the the gravitational coupling at emission and observation, which may make this observation very sensitive to local environmental effects. And so, as a conclusion, in the perspective of closing this Pandora's box, so I mentioned local tests where we test the time evolution of Newton's constants. It's the deviation between matter-matter interaction and matter-light interaction. So the deviation between speed of light and speed of gravitational wave. So there is this hope that with the forthcoming gravitational wave experiments, in particular via the observation of stellar sirens, we may be able to observe a time, or to constrain a time evolution of this gravitational wave equivalent of the Newton's constant, or the here or here. But it will depend much on whether environmental effects are important in the inhomogeneous universe. And this calls for, I think, for follow-up studies about what would be the amplitude of these environmental effects. So my take-home message is that, like in many places in current cosmology, inhomogeneities matter. And we have to go beyond the standard model of cosmology, even at the theoretical level, if we want to be to interpret in a correct way our observations. And with this, I thank you very much for your attention.
Thank you very much, Pierre. That was a very nice talk. So now we have, thank you, Pierre, for giving us the opportunity to ask questions several steps in between, but as you saw, we are used to our good old habits. So now is the time to ask questions about the whole in general. So I remind you that you can raise your blue hand in Zoom if you want to ask any questions, or if there are not so many hands, you can just ask directly. So do we have any questions? Yes, we have one from Nastasia. Go ahead.
Hi, Pierre. So thanks for the really very nice talk. That was very understandable, even though it's a talk on modified gravity. So, so I just want to ask, okay, you said that gravitational waves are lensed the same way as light, and we can apply the same formulas and so on. But so can you comment a bit on what are the observational consequences of gravitational waves being lensed?
Right, that's a very interesting question. It's a topic that interests me a lot, although I haven't worked yet really directly on it. So one thing that I would like to mention, because you talk about it, there is this very interesting paper that's been published a few weeks ago, a couple of weeks ago, I think, by José María Ezquiaga and Miguel Zumarracarregui. And so here they considered the lensing of gravitational waves in these in alternative theories of gravity. So in that situation, it just gives me the opportunity. I'm moving a bit aside your question, but it's the opportunity to talk about that. I think it's an interesting phenomenon. When you look at theories of gravity where gravitational waves are not necessarily propagating at the speed of light, what may happen is that you can have birefringence of gravitational waves. So different polarizations might propagate at different speeds. And one of the potential manifestations of that is that you will have gravitational waves that you receive with an echo. So we'll receive a first gravitational wave, and then a second one with a different polarization, but with exactly the same waveform. So why I'm talking about that is because these kind of things may also happen if you have lensing, even in general relativity. Because one property, when you have a strong lensing of gravitational waves, so the situation where, for example, with electromagnetic signals, we would have two different images of the same galaxy, for example, or the same source, you know that there is this time delay between the reception of signals. So the same thing will happen when you have strong lensing of gravitational waves. You might receive first a first signal corresponding to a first image, and then later a second one coming from the second image with a different amplitude. If these waves, if the time delay is long compared to the duration of the wave, so if you think of gravitational wave lensing by galaxies, for example, so where the time delay can be of the order of weeks and months, then we would have such an echo. But if we think of more like micro lensing of gravitational waves, what may happen is that the two signals will overlap and scramble a bit their waveform. So these are observational consequences. Of course, there is also the thing that you know very well in lensing, because I know you work on that. There will be the amplification of it. So in the same way as we have amplification of the apparent luminosity of galaxies by lensing, we would have an apparent increase of the amplitude of the gravitational waves because of that.
Thank you for commenting on that.
You're welcome.
Very good. Next, we have Prasenjit.
Hello. In the last part of your talk, where you talked about the environment dependence of the gravitational wave distance, inside that square root term. When you said it's sensitive to the environment, is that sensitivity arising from the scalar field, or is it something else?
Well, so the truth is that I have no idea, in the sense that to me it's quite blurry in my mind. But let's take a simple example. Let's forget about screening mechanisms. Let's suppose that these scalar fields could be generated. So there are a class of theories. Sorry, I'm going back to make things clearer. In a subcategory of these theories, for example, the Brans-Dicke theories, the Jordan-Brans-Dicke theories, you may see the scalar field a bit as an additional gravitational potential, in the sense that it would be generated by overdensities of matter, just like the gravitational potential is. It would satisfy a Poisson equation, basically. So in that case, it means that you would have a correlation between the gravitational potential that is experienced by the gravitational wave emitter, so where it is within the gravitational potential of the galaxy, for example, and therefore the gravitational signal that it emits. If it's close to the center of the galaxy, the gravitational potential and therefore the scalar field will be in a deeper part of the well, and therefore it will change that quantity and therefore what you observe. So this is what I meant by environmental effects. It will depend on where your emitter is with respect to to the center of its galaxy, whether it's close to a big object, whatever, and if they are screening mechanisms, I have no idea. It will depend on how the galaxy is screened, whether it is screened. It depends also on whether the black holes that are compact objects will change very much the dynamics of this scalar field. So the truth is that I've got no idea. I think it's a very important thing to study if we want to have any quantitative criterion to give in this context.
So in Einstein gravity, there is an environmental effect, reasonably well understood one. So for example, in the neutron star merger event from 2017, that doesn't give a Hubble constant because it is largely dominated by the environmental effect. But that is expected to disappear as you go to larger redshifts.
That's a good question, actually. So which environmental events are you talking about? Because I thought that so I don't know the error budget of GW 170817. If you do, please tell me. But it will not be lensing, for example, because it's too close for lensing to be important. Is it peculiar velocities? I don't know.
It would be peculiar velocities, and kind of roughly anything within 100 megaparsecs. It has the peculiar velocities dominate, and I think.
But is that the main source of because I think that there is still a quite big error on the actual distance measurement. So it might come also from the analysis of the gravitational signal itself.
There is, because the signal to noise from the third detector was lower, but those problems will disappear, and we'll also go to in the future much larger redshift ones. So I'm wondering if you still see an unexplained environment effect when you go to much larger redshifts and much better signal to noise, whether that could be an indicator that there's,
yeah, that's a very good point. So in some sense, if the environmental effects wash out completely the time evolution, or even if there is no time evolution, there would be this would be a way. So through, for example, the dispersion of the data to infer an idea of this coupling between an additional scalar field, for example. So this is a very good point. At very high redshift, if we control our systematics and that there is that on the top of it, that might be a reason. Yes.
Thank you.
You're welcome. Thank you.
Very good. So next we have a question from Joseph.
Yeah, thank you. First, thank you for a great talk. Maybe if you could show the last slide, please. There was this ratio that's hopefully gonna be measured once, or yeah. So do we have any estimate what it should be in order to like see that these nonlinear effects are really relevant, or can it happen that once it's, I don't know, very small, like 10 to the minus 15, like the velocity below?
So, I'm sorry, are you talking about this ratio?
Yeah, exactly. So once it's very low, does it mean that these non-linearities are not actually so important, or there are some other effects that could be additional to the standard theory? Thank you.
Thank you for the question. Okay, so I'm not completely sure that, so I'll try to answer without being well, in the wrong place. But in terms of what value of this thing, which value we could have. So this, we don't know yet, because this is, you could consider that a free parameter of the theory. So in principle, there is, it's kind of free. It's the idea would be to try to constrain it. Now, I talked here about a specific class of theories that are these Horndeski theories, but there are other theories that would imply such a time variation of this effective gravitational constant. One of them that's been advertised quite a lot in that context is this non-local model by Michele Maggiore in Geneva. So there is such a phenomenon that could happen, and it was shown in the recent papers of Michele's group that the effect could actually be very important, is that there could be an order 1 change. I mean, in the Hubble diagram going to redshifts beyond 1, 2, 3, we would see an effect of order 1. So this is in a slightly different context, though. See, what I've been doing in this work, it cannot apply to these classes of theory, because I don't know how these theories are working in the inhomogeneous universe. Now, it's okay. Well, before I move on, so was that your question, or was it something a bit different?
Yeah, in principle, like the question was whether, if this ratio shows to be very small, if this like class of theories are like just not very useful, or is there any additional value?
Yes, right. So that's okay. This is a very interesting question. Okay. So it's not easy to answer it, though, because there is a whole, so there is a lot of activity in this question of modified gravity and how to test it, especially in cosmology. So one debate is, for example, whether we could apply the, okay, no, sorry, let me go back. One thing that's been interesting people a lot in the context of modified gravity is the theories that would yield what we call a self-acceleration. So theories of gravity where we would have an accelerated expansion of the universe without having something like dark energy. So in a sense, there are theories that allow the universe to be in accelerated expansion without, so just by modifying the way gravity acts, not with dark energy. Now, these theories now are very well constrained, especially because of that observation here. It turns out that in the theory that we know, scalar tensor theories that we know that are self-accelerating, with all the constraints that we have, this one tends to kill the self-accelerating models. So from that perspective, most of the community now seems to accept that self-accelerating models are ruled out and not very interesting anymore from a cosmological point of view. So in that context, now, if we accept that conclusion, this would come more to try to detect some small variations, some small deviations with respect to GR, but not necessarily constrain models that would still explain the accelerated expansion of the universe, if that makes sense. I know it's a very, I think this whole subject is so rich that it's hard to distinguish between the conclusion, to know what are the things we can take for granted, what would be questioned by screening, for example. So I tell you what I think I've understood out of the community, but yeah, there might be people who are experts and who would say that they disagree with these conclusions. So to me, the interesting thing is that, and I will stop on it, but to me, the interesting aspect or motivation to test such an evolution is just to determine whether we are in GR or not, which I think is a valuable question in itself.
Yeah, great, thank you.
You're welcome. Thank you.
Very well. And then we have Joachim.
Sorry, yeah, thanks for a very thought-provoking talk. You mentioned something that I found was very intriguing, which was this breathing mode in the gravity wave, which I think, if I understood correctly, is coming directly from the scalar field wave.
It does.
And, I'm wondering if maybe it's extremely difficult to measure this. I'm not familiar with the details, but if such a thing was measured directly as a wave, as opposed to the kind of tidal type of wave, what would that imply for such theories?
That would imply that we are not living in general relativity, which would be a huge thing. So in itself. In experiments like LIGO, Virgo, but also in the future LISA, the attempt to measure additional polarizations that wouldn't be this plus or cross polarization is one of the major things. It's one of the things that the detectors are trying to observe, even in a theory-independent way, right? Just looking at whether you would see some other polarizations in the signal. So if one day we observe one, that would be a fantastic, that would be great news in the sense that it means there are many things in gravity we don't know. And so, yeah, these would be measured. These could be measured in principle with interferometers. So not if the wave arrives, if the wave plane is parallel to the detector, you wouldn't, because the breathing mode will just change the effective length of the arms without changing their relative length. So you can see it only if the incidence of the wave is not, is inclined with respect to the plane of the detector. But in general, you would see it. And even the other one, the one that would be triaxial, you could, in principle, see it. So yes, this is part of the investigation, of the observational investigation.
Yeah, thanks. That's very exciting. Yeah.
Yes, indeed. And if there are no other questions, I will ask a last one, if I can. Just a technical one. So you split in background and perturbations. Do you make any assumptions about your background in these computations?
No. This is, I think, what was really new in our work, and this was important for me in the perspective of what interests me in in cosmology. I really wanted the background to be completely agnostic, in the sense that these gravitational waves that I treated here, they propagate over a background that could treat cosmology, vicinity of a galaxy, vicinity of the solar system, with one assumption though, which is the iconal approximation. So there is actually one restriction, is that I assume that the underlying gravitational fields are not evolving on scales that are comparable to the wavelength. So in the vicinity of a black hole, for example, that doesn't work. And this is a bit more restrictive than the usual iconal approximation that we are making with light, because the wavelength of light is usually much shorter than the wavelength of gravitational waves. If you think of the gravitational waves that will be observed with LISA, say the one that correspond to the merger of supermassive black holes, the timescales will be extremely long. So in that case, even the solar system could not be really treated as a background with respect to that, because you would have wavelengths that would be comparable to an astronomical unit.
Right.
But that was general.
Right, but then this would require a dedicated full wave analysis, which is then much more complicated.
Yeah. That would be, of course.
Yeah.
Oh, while
it would not be that general in your conclusion. Yeah.
No, yes, indeed. Yeah. Let me, because you say that, I would like to stress one of the advantages of having, worked with a general background is, okay, so it's a bit. The problem with animations that you cannot skip them. I wanted to go in that conclusion. So I will stop then with that, but I think this is important. Okay, right. Yes, so what I found interesting with the fact of working with a general background is the fact that this gravitational distance seems, it depends only on the emission and the observation points. It doesn't care at all about what's happening on the way. And I think this is a very important result, right? People sometimes talk about gravitational wave friction when talking about the evolution of the amplitude. And this is not really a friction, because it's completely, you don't care about so even if you had a very strong gravitational field here and strong lensing or whatever, you don't care. The gravitational wave sees it, recovers its properties, and then you observe it depending on only the emission and the observation points. And this is true for any background. I think this is kind of interesting.
Yeah, it's very nice indeed. Okay, very good. So are there any other questions? I guess, Joachim, your hand is just still raised from last time. Very good. So if there are no further questions, let us thank one last time our speaker. Thank you very much. Yeah. And that's it. Thank you very much.
It was really a pleasure. It's really nice to have so many questions.